Hello, everyone, and welcome to Handmade Hero, show where we code a complete game live on stream. I today actually am just going to do what I said I would do in on the Twitter I posted in the middle of the week, or not. You know what? Actually, it wasn't the middle of the week. I think it was like right after the stream or something, or I don't know. But last Sunday, we had tried to put in some debug visualization of the lighting values at various locations in the lighting voxel, and they were just like wildly weird and wrong. And during that stream, I said, even as I was debugging it, in fact, there was a whole section of that stream where I was just lamenting how bad programming languages are at managing indexes, and how if you want to actually have some protection or guarantee that your indexing schemes are right, it requires writing all of this additional structures and code that just like piles up and is a waste of your time. And what you really want is some way more efficient way of checking your indexing to make sure that you're doing it consistently. And I said, I bet this bug is going to be an index bug. And then maybe, I don't know how long after, a day after, or maybe it was only a few hours after, I don't remember. I was sitting on the couch and I realized like, oh wait, it just kind of popped into my head. I was like, oh, I know what our bug was. And it was exactly what I said it was going to be. It's an indexing scheme bug. And I posted a link to the line of source code. So what we're going to do today is just talk about, well, we're not going to talk about it. I guess I'm just going to show you what it was. And then we're going to go from there. So if we get our drive subset first. And also, I'm kind of like a little bit off kilter here. My keyboard is not set up the way I would like. Okay. So if we go ahead and load up Handmade Hero here, I can show you, well, first I can show you what the bug actually was, which I don't know if where we left the compile. So I may have to flip a few switches on the compile to get us back to where the bug actually was. But I can show you what the bug was, and then I can explain why a simple indexing error produced this bug. So you can see this is actually the lighting solution from the previous round. This is not the grid ray tracer. We're in the process of deving it. This is the old AABB tracer, and you can see that the lighting in the world is relatively correct. Like as I move this one light, the light is this cage is being drawn around the light there. As I move this light around, you can see, that it responds the way you would expect. Lighting-wise, for the most part, we, haven't done a lighting quality pass on it, so there's probably some issues with it. But it's not nonsensical. Like you can see that the light, behaves relatively sanely as we move throughout the environment. When we look, however, at the debug values, you can see that they make like effectively no sense at all. So looking at these values, you can kind of see that as I, just sort of look at their directionality, they're pointing in completely nonsensical directions relative to the light source. So, I just don't know like what's going on, right? And that's where we left the stream last time. I was like, it's really weird. And I tried to look, at a couple things that maybe could cause that. We didn't find anything. And I said, this is going to be an indexing bug because all bugs that take, more than 30 minutes to solve are indexing bugs. And, that's exactly what happened. At least I think so. Maybe I'm wrong. But if we look at what was going on here, my realization, and I won't quite pull up the code yet, my realization was, wait a minute, we're trying to draw a subset of the grid, but did we ever actually offset our sample? And what you can see, if we go look at the actual code now, we made a special piece of code for this. I don't really remember what it was called. Let me take a look at the functions. I think it was just like debug. It had debug in front of it, and it was like draw maybe octahedral values. It's this. So if you look at what happens, you can see we're looping over the XYZ of the debug dim. So that's the region, that's the size of the region we want, which is a quarter of the voxel. We are producing the coordinates by taking this vox start value and looping over it, right? But then what you can see here is when we go to draw the value, look, it's just XYZ, right? So we're using a 0-based offset to pull the lighting values out, but we're using an offset value to draw them. So we're drawing them at the right place, but we're loading them from the wrong place, right? And so we needed to do this, right, in order to get the correct values out of our system. Oops, those should be lowercase. And so again, assuming I'm right, just a simple indexing bug leads to something that's very hard to troubleshoot because either you think of looking at it or you don't. So once we've made that change, hopefully you can see now we're actually getting very sane results out of the system, right? So you can pretty much see like all of these lighting values coming and they're pointing back at the light source, which is what we would expect. We probably want to constrain the length of these values a little bit more than we are right now. We had kind of just played around with that while we were working on it because we didn't really know what was going on. But now that we have a sane effect, we can truncate these lines to something a little bit more sane so that we can just make sure that we're only really looking at values that are within the range of what we expect for the lighting will be drawn with a reasonable size relative to their grid. And so you can kind of see as I hop around now, the lighting values actually make perfect sense. You can see now that when we look at the direction of, remember these octahedral maps are encoded in such a way that they point in a direction and say how much light is coming from that direction. And these lines are just drawing the values of those octahedral maps. That might be, I don't know how I feel about that. That might be fine in terms of lighting size. I don't know how we want to look at it, but so now what I might do is go ahead in as well and just to make sure that everything is sort of kosher. In our room generator, we turned off the lighting, so we didn't have anything in here that would add lights to the system, whereas before we did. So we only had the debug light. Here is a system that has multiple lights. So basically, like you can see now, there's a number of lights hovering around. And so, looking at this, I guess I would say, I don't know if, I can't say that looks particularly convincing. I mean, you can see that there's a little bit more there, but it doesn't really look like we're getting much lighting from some of these ancillary lights, not as much as I would expect anyway. Maybe they're very dim, and I guess that is kind of true. Like if I look at the lighting there, there's not maybe as bright of a patch as is around me. So it could be that it's just a little bit of that in the mix. Let me move over here a little bit just so we can see. Well, I guess I don't know. Maybe I can't. So you can kind of see there as I move through here, yeah, there is still light coming from there. And I just, like I said, don't really know if that's just because those light values aren't enough. I mean, you can sort of see that it's coming from there. So I don't know. It's not obviously correct. I'm not psyched about it, to be completely honest. So it's hard to say, I couldn't really tell you if that was right or wrong. I mean, maybe it is, I don't know. So hard to say, but whatever. At least at this point, I feel a little bit more confident that we're drawing the actual values, and that was really the part that I wanted to get to. Let me see what happens if I jack up the lighting value here. So if you look at add piece light, oops. Well, it's probably right here, yeah. Here's our values. So here's the radius, here's the location relative to the base, and here's the emission value. So I don't know, like, what's our debug light? Because I don't know. If we go to the world mode and just look at the debug light part. So where does that actually get recorded? So what you can see here is this does a push light and it just pushes 111. So, I'll be honest, I don't quite understand why the emission levels there would be. Oh, well, okay, so actually I guess I do. If you look at these numbers, these are not 111. So I guess the lamp does have like a lighting color associated with it. So I suppose that's maybe where that comes from. So if I doubled this, it would be back up towards a 111 light. So maybe we can look at that and see what that looks like. So there you can see a little more clearly that there is light coming from that direction. So maybe this was just that these lights were a little too dim to show up in the system as well as, as the debug light. Yeah, and so that's a little bit clearer. You can see, getting more light gathering from this, from here. What I will say is that you can kind of see, however, that there is a fair bit of just overall bad targeting, and this is one of the reasons that we sort of had that brief thought, and we put in a little bit of work towards it, but it was never really quite something we wanted to do particularly specifically. But you can kind of see that for lights that happen to have sphere values that are very close to where the thing is, then you hit them, and other ones don't. I wonder if we might need a denser covering of the sphere to ensure that we actually hit these things, because right now we may just not be producing enough, right? Like we may not be producing a sufficiently large number of shots in that direction. You know what I'm saying? So I think the important thing here is just to is just to remember, okay, we don't really know to what extent we're doing a good job with targeting and or with any of those ancillary parts. So let's just keep that in the back of our mind, and we may want to augment some things to improve that behavior. But otherwise, I do think we're roughly okay here. Like this looks better. But I definitely think there's improvement there. The other thing that I think is this, to me, argues that maybe our Cubecaster as well can definitely be a much better solution than the AABB one. And the reason I say that is because that caster, the Cubecast, the Voxel, the grid stepping one, the grid stepping tracer is capable of doing things like bucket brigade movement of lighting from cube to cube that this tracer is not at the moment. Although I guess we could augment it to do so. And because of that, I think we'd have a better time of taking hits to bright lighting and moving them backward, so propagating them to other squares. And that, I think, would be a good improvement, right, over this system. So I think we've got what we want now, and so I think now the main thing we need to do is start the lighting quality work and get the Cubecaster working well. And we may have to do some debugging of specifically the Cubecaster. I don't know if there are some bugs in there at the moment that are causing us problems. We know that we're getting way too bright results from it, but we don't actually specifically know why. So it could be, and you can kind of see here what I mean. When we switch to the Cubecaster, the numbers drive towards infinity. So they keep getting larger and larger and larger and larger until they're just, basically, IMF or whatever. They'll there's a positive feedback loop that just adds energy to the system effectively forever. So the question is, what do we do about that? Because we don't really know exactly where that feedback loop is coming from, and we don't know to what extent that feedback loop is just the result of us not having gone through and actually done the lighting quality pass where we've managed the values properly and know what they all mean and how they should propagate, or if it's just a case of there's bugs in the actual cubecaster that themselves are creating artificial feedback loops or positive energy injection that shouldn't be there, right? So the key thing here to understand is that we don't really know what kind of bug we have yet. And so we're going to kind of start the lighting quality work. But the reason we're starting the lighting quality work is not because we think the cubecaster works. It's because I don't think there's any particular way that we can debug the cubecaster's current issues without actually knowing we have a more robust definition of what should be happening to the light. So we need to start working out real measures of what we expect to happen and a solid definition of how it should happen, because without that, we're never going to be able to debug the system. That's what I would argue, because something like a positive feedback loop can just as easily happen from a poorly thought out mathematical scheme for distributing the light as it can from just a straight up bug. So it could very well be that this system is working exactly as intended, and maybe it's just a better system for gathering light than our previous caster, and it just exposes an underlying mathematical issue with the way that we're treating light, and it's expected that it should blow up the way it does, right? And so differentiating between those two scenarios is our goal now. And so we want to have ways we can visualize what's supposed to happen. And that's why I started, that's why I wanted that drawing. We also added something that I think will be very useful. If we go to the world mode code, I also have an F key pressed thing in here where I could do F9 each time to update the lighting. And so that's another thing that we're probably going to want to make use of and just augment. So if in here I hit F9, what you can see is here is, first of all, an example raycast, which is useful. And second, you can see the lighting values after one step of the lighting propagation. And the game is still running, right? But it's just not running the lighting solution. It freezes the state of the lighting solution in place. And then I can go ahead and I can just step, right? Single step the lighting each time. And you can see the light propagate through the world via the cubecaster. And so there's a couple things that you can see happening here. And I guess what I would say is even just that is probably sufficient for me to see a particular type of what I think is a bug, or at least something we have to rectify. And it's probably where we should focus our attention first, because it will be the most straightforward place we can measure our success. So if I run the game and I look, and I think, I should do this. And I think if I go back to if I turn off all the lights, so we can just simplify our problem. So turn off all the lights except the one that's just centered around the hero. So exactly the way we started the day. We go back there. So if I start there, what I should be able to do now is in the game itself, I should be able to single step the lighting. We know that all the light's coming from here and distributing out to the cubes. As I step it, what you can see is you get the lighting from these parts bleed through the wall quite dramatically, right? So, as I'm single stepping this, you can see the light leaking through the wall and, moving bucket by bucket sort of forward. And that's what's going on here, right? Like this is hitting, these raycasts are hitting here, gathering light from here and moving them backward, right? You can sort of see that happening. Right? Now there's a couple things about that. So the very first thing that I think is clearly buggy about this, and so what I'd like to look into first, is let's take an example of how that would have to happen. So if you imagine going back to the original lighting solution, I should put in a key for clearing it too, shouldn't I? So if you were to look, for example, at specifically maybe like this part, and I guess it's a bummer that I can't see those. I should probably like clear the depth buffer at some point here, and so that I can see these drawn through where the occluders are. The other thing I could do is just not put them on there. So one thing I could do is in the world mode, in the entity system, one thing I could do really quickly is just turn off the drawing of the cubes themselves. So when it adds an occluder, I'll let it keep adding the occluder, but I won't actually draw the actual thing itself. So let me see. I don't know how easy that is to do, but I'll take a look here. So it looks like the way that... it looks like this is the draw sprite code, which I don't care about. So it's really this. So here's me pushing the occluder. If I just don't push the cube, right? What I should see is all of the sprites will still be in the world, but the cubes just won't be, right? And so that allows me to sort of see through the walls here. So here's where those wall points would be. And as we run these, what you should hopefully see, right, is that, this is just garbage. I mean, this thing is inside geometry at the moment. And, it's getting light from here somehow. I'm not sure. Like, how did it get information that light was coming from over here? I just don't know. And I guess that kind of, if I look at the distribution of who is having these sort of ridiculous ideas about where the light's coming from, it seems like kind of overwhelmingly people who are embedded in geometry. And it's not necessarily a bad idea to let people embedded in geometry cast out from that geometry, which I believe we do allow currently, right? Like you can cast outward, which is what's supposed to happen there. But, more specifically, let's do something else real quick too. Let's take a look at what happens in the non-grid lighting for that exact scenario, because I'm curious. So here's the non-grid version. And it's like, at the very least, you can see that those do not record light coming from the other side, right? So at least what it sort of suggests to me, and maybe this is just a trick of the eye, but what that sort of suggests to me is that we should take a look at what happens when we're casting out from inside things, because I have a couple ideas of how that probably would create issues. And in fact, I think we may even want to, we may even want to make a special code path for casting out from inside of things. And the reason that I say that is because we do need interpolants for everywhere in the world. Like, we need to be able to know what the lighting values should be as they blend, because it's a sparse sampling, right? I mean, it's a sparse sampling of stuff here. And so we kind of need to always have a sample, even if that sample is erroneous. Is in an erroneous location, someplace, or I should say impossible, like a place where you can't sample the lighting because it's inside geometry. But what I'm thinking is happening effectively is, these cubes, let's say I draw them just so you can see as for an illustration. Let's suppose I do, instead of a push cube, if I just do a push volume outline. Because I think I kind of am starting to get a better idea of what's happening here. I don't remember what that takes as parameters, so let me just take a look here at what it actually wants. So it takes a rectangle and a color, and that's really all I need to specify, I guess. So if I was going to do a push volume outline, it would be a rect center half dim on those two parameters, no bitmap ID, and the render groups. So I think that's all I would need to draw these cubes. So looking at what you get when you draw them, here you can see all of the cubes as like a lattice, right? And maybe I should pass like a thin thickness, a thickness of significantly less than 0.1. Maybe I do 0.01 here or 0.025, just to make it a little easier to see. Those lines were a bit overbearing. So if I draw the grid here, you can see where we've placed these volumes and what's going to happen. And then if I do the F9 to step the lighting once, so when we start to look at what's going to happen for these lights that are contained here, so here's what I'm afraid of and what I think might be happening. When this, it casts outward, yes, we may have written the code properly so that it will allow you to cast out from a volume like this, because I believe we ignore hits that are in the same facing direction as you. We may not, and so that may be an additional bug, but let's suppose that that was correct. Even if we are handling that correctly, when this casts backward in this direction, it will hit this face of this cube. And because we are not respecting the fact that this occluder will prevent us from going backwards, we're going to record that as a hit, and we're going to sample the lighting from here going that direction. But we never should have been able to sample lighting coming from that direction, right? So when we are inside something, I think what we probably need to do is we need to make sure that when we are going to sample the lighting, we just sample the lighting going in the same direction as we cast. In other words, we just want this to have the lighting value that came from this direction, because that's what this square will have, and we just want that to continue probably. Or, I mean, maybe we just want things inside to be 0 is the other option, right? Maybe we don't want them to have anything in particular. But either way, just treating them as nothing, I don't think that's going to work. So we may need to consider what to do when things are inside, and we may need to just nullify them. I don't know. But I think that things inside existing structures, I think we're going to have to take certain care to just do something different with them. So again, I really don't know what the best plan is for that. But I think the first thing I'd like to try is let's start by maybe just zeroing those. So, you know, at the head end, before we do our raycast, we just check the square before we start any raycasting on it whatsoever. And we just, if that cube's inside one of our occluders, we just zero it. You know what I'm saying? We just blend in zero lighting at that point. I'm not sure that's the right answer. That's what I'm going to try. And if I go ahead and remove the in here, if I go ahead and remove the world mode stepped lighting, so we just do that. If I remove the stepped lighting, I should actually, you know what? That's not the right way to do it. Why not just do it this way? So if I go ahead and remove the step lighting and let this run and do its sort of over brighting that happens. Oh, well, no, sorry. We have to also switch back to the grid-based lighting. I'm going to go see what happens if I add something to nullify all the stuff that's inside the walls, just to see what effect that has on at least the light leakage. So I don't suspect that will necessarily help me with our lighting growing without bounds here, but this part here where this leaks outside, I'd like to see if that starts putting a damper on that process, and it might not, but we're going to see. So in order to do that, I think the most effective way is inside the lighting system. I probably want to make it so that I just ideally don't want to spend any time thinking about those. So I think I want to do this as a prepass that basically says, look, when we dispatch to do a full cast on a cube, so, you know, if we look here. So if you look, all of these are going to come from the same location. So we pull the ray origin out of the light probe p-value here that we're getting. When we do that, I think what we're going to want to do is do the check right here, right? So we'll want to take this light probe P. We already know, because when we come through here, we're literally going to pass exactly where you would start your grid walk. So we know what the grid index is for this location. That's just a known quantity, right? In fact, we have it right here. So if we know we can load the initial grid index, we should be able to do a prepass on each cell just for the cell itself and check to see whether we're inside. And if we are, we can take a different route and avoid the entire grid cast altogether, which will probably actually save us time in the grand scheme of things. I don't know why I'm looking in the wrong file. So if we take a look at the grid raycaster, which is right here, you can see this piece of code where we loop over the leaf indices and check them. So here's an example of that code. What I'd like to do here is say, once we've pulled the ray origin, which is just this light probe p-value, we're just going to go through and we're going to check to see if the light probe p-value is inside one of these boxes, right? So we don't actually need all of this nonsense here. We should be able to do this by just directly taking the comparator and saying, are we inside? And if we are, then, you know, we can literally just go if not is inside or something like this, right? And we will just not do anything if we're not, right? So if we're not inside, we wouldn't do anything. Now, that's not exactly correct. We would rather, at that point, write zeros in. And if we look at the way that we're updating the parts of the map, we still kind of need to do this process, right? We need to pull the texels here and update them. So we may want to do something more like this in the long run, but right now, because these things, and just to be clear, we don't care about this when we first start, because we aren't moving any of these not the voxels. We aren't moving the volumes around. So because we're not moving the volumes around, if something's inside, it will just be inside always, and if something's outside, it will be outside always. So we don't have to worry about the case where a voxel cell was getting values and then it's not. But we don't know that it's always going to be that way. For all we know, we may have a bunch of levels at some point where we are going to move those around, which will mean we'll have to handle extra stuff. So we may say, like, so we may need to do a lerp towards 0 scheme here where we make that happen. And again, like, I just don't know how we want to address that, but we're going to have to do that. And furthermore, I don't know if we actually do our clears properly. We might. In fact, I think we do. So I think we're fine, even though the grid moves around. I think we're fine because we do clear it. But the point is, we want to handle lerping towards 0 here in case we ever have moving occluders, which, you know, we might want. And there's probably other work we'd have to do to make moving occluders not look stupid. But again, we just want to make note of that. So at the moment, I won't actually do that. And all we really need to do is look at this routine. When we come through here and we have this ray origin, now we have a box min and box max. All we need to do here is do a comparison. We want to know if this thing is both inside is less than the min. Greater than the min, less than the max. Because if our ray origin is less than the box max and it's greater than the box min, that's going to give us, and, you know, honestly, I guess I don't, I guess I don't know if we have these operators, but it, excuse me, still having coronavirus problems. I don't actually know if I have coronavirus. Basically what we have here is a test for each of the bounds, x, y, and z, each across 4 lanes. And what we need to be able to do is we need to be able to collapse the x, y, and z down into one set of lanes, and then we need to look at what the mask actually tells us. And as long as we're inside on any of them, then we're inside, because each one is a different box. So we should be able to just do a single move mask and record that value. So if I say U16 is inside equals 0, we should then have what we need. I just have to collapse it down. So if we go ahead and say, well, there's an F324X mask, oops, and that's inbounds X or inbounds Y or inbounds Z, or sorry, not or, and. That should give us what we need, I think, right? And don't quote me on that. Now, We don't actually have the node that we're looking at here. Is there? It's complaining too about this. So we don't have one of these for the v34x. Well, you know, I guess I don't know that I care about writing something like that. I mean, we could, but I think this is fine. Right? Because again, we don't really even know how we want to do. We might want to try and do this in a more efficient way. I mean, who knows what we're going to do in the future. So I'm not going to go make an operator just for that because I'm not sure I really need it. So I'm just going to do the testing here where we do inbounds x, y, and z. And then we get the mask and we AND it together. Right? And honestly, you know, that's probably, I haven't actually looked to see if that's the smartest way to do that. It may be that you actually want to do 3 moves and do the AND separately because you're in a loop and blah, blah, blah. Like, this is not performance critical at the moment, so, you know, we'll leave that for another day. But at the moment, what we need to know is, what is this node, right? And so if you take a look at the way that we were doing it before, you can see we want to load up the node from something. Oops. And the answer here is that, well, we actually get past what the grid index is that we're starting in, right? So we should be able to just do this is-inside testing very simply. And that should allow us, if we go debug this code path, that should allow us to stop getting those values, getting anything set on them, right? And what you can see there is actually, although eventually the light did penetrate through the wall, you could see that it actually held off for quite a bit longer. So I think this is starting to, I think that probably did work at least a little bit. And let's take a look at it in single step now. Oops. Where the heck did I put this code? Wasn't I right on it before? There it is. So if I go ahead and single step now, and just take a look at how that propagation is working. So let's take a look. Here's our grid, and I'm going to do the first pass. So hopefully what we'll see now is as we go, these, well, those are outside, so they should be okay. But these along the wall here should get none, right? And no matter what, even when these explode, these should never get anything, right? And it looks to me like that's exactly what happened, right? So that seems really pretty good. Right. Yeah. So I'm pretty pleased about that. I think that's really good. I think that's a positive step. I think we probably want to keep that. Now, what I'd like to do is really quickly, just so I can see what the effects of this are, since we know that our other raycaster gives a better approximation towards usable lighting at the moment because it's more debugged. I'd like to go ahead and see, well, all right. So I can't really, I wanted to just try the other raycaster, but I guess we can't because we removed the entire path, which was the thing we would need to do the testing. I just wanted to see what would happen to the lighting in that case when we knocked those out, just to see what it looked like. So what I would like to do now is focus on the actual light directional propagation elements, because there's a bunch of things I'm seeing in here that make me suspicious of how we're doing the sampling. Now there's a couple of things we want to look at. If we take a look here at these light values, so another thing I can do is I can turn off this now. And the reason for that is we know now I've visually verified, as well as having the code in there, that people on the interior will get set to 0. So I think I can safely go back into the entity code now and remove this volume outline switch so that we can just see the actual world again, because I know that anything inside that I can't see is going to be 0, whereas before it wasn't. So that's a good step. And if we take a look at what's going on in here, I guess one thing I would also say is it's looking pretty promising too as we go. I mean, you know, we're a far cry away from having good lighting, but you know, if you gave me this, what I'm looking at right now, and said, you got to get that to a really good lighting solution, I'm like, wow, we're almost all the way there. Like, we really just need some better, like, spreading interpolation to hide that voxel boundary a little bit more. But other than that, like, we're in really great shape. You know, I look at that and that just looks awesome, right? So I don't think we're that far, and I think we're going in a promising direction, but obviously we still have a bunch of things to address. So the first thing I'd like to say is, let's start looking at this, because this indicates very clearly to me that we've got some issues. When I'm casting up through this, you know, this wall floor panel, this raycast, we at least believe, and you know, we have inspected many of these, and it does always seem to produce the correct answer. You can see here. The normal that our raycaster has been producing seems pretty solid, and I'll do another verification where we'll try looking at this, and we'll see if maybe these normals are wrong. But I'm assuming that if we inspected one of these, we would see the normal facing back at us, right? And if that's the case, that means we're asking what light is coming down this way, right? And the way that we're... sorry, that's not true. If we're looking at the sample here, right, that means we're looking at what light is coming from this direction, so the downward facing direction, right? And I guess the problem that we're going to have, and I don't really know, I mean, it actually just looks erroneous to me, but I don't know, is when I look at what is supposedly coming from that direction, there's not much light there, right? Now, part of that may be, I think we're still drawing the spec map. And I don't really know, right? I mean, it could be, but I'm not sure. So if we're still drawing the spec map, and let's take a look. What happened here? Why can I not see? Did I delete something? I'm like stuck over. That was weird. I was like stuck over on the other side. Let me go ahead and jump to the lighting code here. There we go. So if I do the draw octahedral values, you can see me here drawing the spec atlas. So what I'd like to do is I'd like to draw the other atlas as well. And in order to do that, again, I have to fix this bug that we had in both places, right? So we're wanting to use the Vox chord for each case. So if I was to draw, specifically draw the... If I was to specifically draw the diffuse atlas instead of the spec atlas, what I want to do here is see, is the blurring step creating like way too much light coming from that direction, and that's what we're seeing there, and I don't know. So what you can kind of see here is if I take a look at where this light is going to get sampled from, so here's an example of what it probably looks like. Now, unfortunately, we're not quite getting the exact one, although I guess we are. Yeah, we are, because this is going to cast like upwards, right? And so if you take a look at how this this right here is getting blurred, I guess what I'd say is, you know, it does seem to have quite a spread on it there, and I can't say it's necessarily wrong, you know, but it's definitely dramatically power increasing. And so, you know, I guess I can't really say that I should start debugging these quite yet, because that part alone does look kind of wrong. I mean, I don't know. I guess it's pretty hard to say is my problem, right? I really just don't know what I should make of that. Just to give you a little bit of perspective on what I'm thinking. So when we're going to produce the updates for this, right? So you can see as that grows, like what did it look like? We're going to get a normal that comes back this way. And so what we're going to want to know is for the cast that went out this way, we're going to want to know what kind of light for this location was coming back from sort of straight down, right? The diffuse component of like a straight down light. And so when we look at what that would entail, you know, it's going to be showing, you know, this downward facing part here, I guess, is what we would think was coming from that direction, right? And so I don't really know what I think of. There's a lot of ways that I could go on this, right? So if the first thing I want to do is focus on what's happening to this, there's a lot of ways I could address that. So one way I could address that is by saying every time I go to do a cast, if I'm going to sample from a particular light probe, if the light probe is on the other side of the thing that I've hit, I don't sample it, right? So in other words, when I do the 8 voxel samples, I only sample the things that are on the side of the... so in other words, I would sample these, and I wouldn't sample these, because they're on the other side of the hit. So I know that they can't be included, right? And it's a pretty trivial thing for me to do, like compared to how much work we're doing for all of the other ray casting operations, it's really not a huge deal. And it's just a really tough decision. So if I want to focus on that, that's the first thing I could do. And I suppose maybe we should just do it. It's not a particularly difficult thing to create. It's fairly cheap, and then at least we can turn it on or off and see what's going on there, right? Let's just do that. And then we can maybe see if that prevents... And I guess here's my other thinking, just to give you a little bit of a perspective on what's going on here. Oh, Abner has shown up. Hello, Abner. Are you here to talk about Handmade Seattle? I have not heard anything about Handmade Seattle yet, other than the post I saw from you, so... Did everyone see that? We'll talk about it at the end of the stream, if Abner's around. So, basically this... This environment, in my mind, gives me a good opportunity to actually do the thing I just said, which is why I'm thinking maybe we should just do it now instead of later. And the reason for that is because right now we're in a situation, it's at least undesirable, perhaps it's buggy, but it's even if it turns out that it's not a bug, it's at least, a defect, right? Which is that we're getting this massive overbrighting. But the nice thing about that massive overbrighting is it really quickly and dramatically shows us where light leaking occurs, right? So as we drive these numbers up to be absolutely huge, we can see the light leaking happening down here. And one of the things that we might not have another good, clear opportunity for is seeing light leaking really clearly, right? And so because this is a very pronounced situation, I'm thinking, why not just use it to help solve a light leaking problem I know we'll have anyway, rather than trying to tackle it when it's more subtle. So rather than trying to solve the feedback problem first, I think I maybe will focus on this part. So let's add something to our octahedral sampling to allow us to do some kind of masking. So for example, when we actually do a voxel sample, I don't know what we call it. I think it's just, yeah, compute voxel irradiance app. So when we actually do our voxel sampling here, what I'd like to do is say, if you look at this lerping that we're doing here, and what we want to do is maybe transfer or transform the way that we're computing this to be based on single coefficients rather than lerps. And if you remember correctly, what a lerp does, right? Let me just pop over because, oh no, my pen has gone down. Oh no, where's my pen? It just fell into the depths. There we go. So if I just quickly remind people, because I feel like you can never really remind people enough. So whenever you're doing any kind of a weighted blend, all of these things are linear operators, right? So if I am going to do a standard lerp, like a standard lerp, which is I guess in this case, it's actually a trilerp. So a lerp is just a linear blend. But in this case, we're doing a trilerp. And that's just, 3 linear blends. And the important thing to remember here is that when you're dealing with linear operators, you can do whatever you want with the order in which you process these coefficients. So if I take the linear blend, which is traditionally going to be like a blend between two things, we'll call them A and B. If I want to know the resulting point that I'm going to create is 1 minus the blend factor times A plus the blend factor times B, right? If we look at this fundamental equation, if we start to apply it multiple times, I mean, first of all, you can already manipulate it, right? I mean, you've seen some people will rewrite this, or depending on what you're trying to do with it, you can multiply the A through, for example, and you'd get A minus TA plus TB, right? So you can create different versions of this equation as well. But for our purposes, we only really care about looking at this particular version. And the reason for that is you can see that these two values are scalar values. And we could just rewrite this as a generic weighted blend, right? We could have just said, well, there's a WAA plus a WBB, and we're just doing a weighted blend of two things, and we just happen to know that these two weights sum to 1. So we know that WA happens to equal 1 minus T, and WB happens to equal T, right? But once we start to apply this equation recursively, which is what we're doing in a trilinear blend, and we'll just take maybe the bilinear case for simplicity, we're expanding the notion of this. So rather than talking about two values, A and B, and we're blending between them by picking a t-value, and the t-value, gets us some distance of the way there. So, the t-value gets us to here. When we start talking about, for example, a bilinear blend, we're talking about 4 inputs. So we're talking about A, B, C, and D, for example. And if we're talking about using a t-value to get somewhere, we do it on 2 of the bars. And then we talk about using some other value, an u value. Maybe we use u and v, I don't know. So maybe this is a u value. You can letter them however you want. But that produces a new intermediate bar, and then the second value, let's say v, produces the new point, right? And that's the conceptual framework. So we certainly can do something where we say, well, all right, if this is going to be P0 and this is going to be P1, and then we produce our final P value from those, then we're just doing 2 of these equations. 1 minus u times A plus u times B, and then P1 in this case was 1 minus u times D plus uc, right? And then we took those results and said P is equal to 1 minus V times P0 plus V times P1, right? So this is applying this recursively, but hopefully what you can see here is there's nothing preventing us from just doing the substitution back into this equation. We know that P0 came from an existing blend, 1 minus UA plus UB. So we know that P0, in this case, if we plugged it back in, this would actually be 1 minus V times this whole equation. 1 minus UA plus UB, right? And the same would be true over here. So the V times P1, this P1 is really just this whole equation. It's 1 minus UD plus UC, right? And so if we actually multiply these out, you start to get pretty obvious answers for what the actual coefficients are without needing to think of it recursively anymore. Like this is the recursive formulation. But because it's linear, we can just think of a flat formulation, which is this. Because if you look at what happens, we just have 1 minus V times 1 minus UA plus 1 minus V times UB plus V times 1 minus UD plus UVC, right? And lo and behold, we just now have each of our input points, A, B, D, and C. They're all here, right? And they each have a weight. And that weight is some combination of U and V, either the 1 minus version or the regular version, and we have each of them appearing exactly once. So now we just see that, well, this whole equation is just weight of A plus weight of B plus weight of D plus weight of C. And I could have just written them in order because we don't care what order they come in. They're just terms on a line. So this is just a very simple weighted blend, right? It just so happens that these are formed, the weights are formed by the trilinear coefficients, right? So each of these just becomes whatever it was up here, 1 minus V, 1 minus U, 1 minus V, U, UV, and V1 minus U, right? So you can imagine doing this as many times as you want. We could do a 8-dimensional linear blend if we wanted to, and we could literally do that just by taking all of the input points in our 8-dimensional blend and generating all the weights for them, and they would just be a single sum equation where it's just fmad, 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 right? You multiply and add, multiply and add, multiply and add, right? And so the sum of weighted coefficients will build us any order linear blend we want, any dimensional linear blend we want, whether it's linear, bilinear, trilinear, or any other higher dimensional linear. And this allows us to avoid using that recursive formulation. Now, you may ask yourself, why would anyone care about everything I just said for the routine that we actually are looking at? And the reason for that is because if you flash back to the routine here, what you can see is in the recursive formulation, it would be incredibly difficult for me to figure out how I would produce a reasonable blended result if I wanted to pass in effectively an arbitrary bit field that said which tiles could be used and which tiles couldn't, right? Now, one way that you could think about doing this would be to say, well, actually, no, Casey, it's very easy. What I'll do is I'll just take whichever of the tiles are supposed to not contribute, and I'll zero their value, right? But the problem is that's not the same thing as not using them. That is using them as if their lighting was zero. So all of the lighting will be darker than it should have been because we are actually using those values. We're just using them as if they had no lighting. But that's not what I wanted. What I wanted to do was I wanted to say, build me an n-way blend where the n, the number of things I'm blending, are just the ones that I can use. And if there was only one, I just want you to use that whole one as the value, right? So hopefully you can understand what I'm saying here. Like, we need a way of constructing an n-way blend where we're really only blending between the n elements. We're never even using an element that's out of bounds. Because if we were to just set it to 0, we would get darker, we would get results with a lot less light than we should have, right? But hopefully what you can see is, based on what I just said on the blackboard, you can see where I'm kind of going with this. If instead of doing it that way, where we had the if what we had were individual bit field or weight values that told us what we were allowed to use and what we weren't, then what I could do is take that weight vector, which is 8 weights, which by default would just be exactly what I did back here. So it would just be combinations of UVW, right? So it would just produce the standard linear, trilinear blend we were doing. If I take those values and I knock some of them out, so I just knock them out to 0, then I can use, which we've talked about many times before, the Euclidean 1 norm to say, how do I boost the remaining values back up so that they sum to 1, right? And then what I'll have is a blend that is fully weighted, but only using the actual sample values that I'm allowed to, right? So I can do exactly what I want, and I can actually do it quite easily, as it turns out. So when we do compute voxel irradiance at, let me first translate this routine into something, and you know what, I maybe could do this here. Let me just go ahead and restore our ability to do this. So our is inside can just really be nerfed here. It can just say if lighting use grid, end if there. So we can use our old lighting if we want to. This will be compatible either way. And what I'd like to do is just say, all right, here's what we expect to see as the sampling. I should probably turn back on let me go ahead and remove that so I can just run the lighting and not have to use the F9. Where was that? World mode, there. So if I go ahead and run now, I should be able to modify this routine such that it allows me to pass. And what I can do is I can literally just leave it exactly as it's doing it now by just changing the form of the equation, but using the coefficients that I know the equation will produce, right? So that's the first step, because we want it to be working when there is no occlusion. We want it to be working exactly the same. We want it to be working exactly the same way, so I don't want any difference in value. So I want to change this routine, and I want to use it by effectively taking, you know, essentially the same thing here, but I want to use weighting values. So if we use the tiles here as such, I don't know that it makes a lot of sense to still use the like 2-2-2-2 scheme there. It seems a little bit unnecessary, but I don't know. I guess we'll leave it for now. So if I go in here, well, does it really make sense? Let's just fix that. So you can see here that we're using the 2-2-2-2 scheme. What if we just compressed these values just down to being in order, right? And so 0, 0, 0 comes first, 0, 0, 1 comes second, right? And you can see like these just go in order anyway. I mean, they're already literally in order in here. So I feel like we should be able to just compress this down and say, look, there's 8 tiles and there they are, right? I mean, at least I don't see any reason why we couldn't. And then this would just become this, right? And that just seems a little more sane than trying to deal with 3 separate array subscripts, which at some level is going to be a little bit annoying, right? And so we've packed these specifically, I guess, in this order. I don't know why we chose that order to begin with, but I guess we did. You can see it just goes X firsts always, and then Y seconds, and then Z thirds, and then we did the blend in that order, so off you go, right? So if we were to build now, my hope is that I didn't change anything and we don't get, completely ridiculous lighting results here from all the sampling and whatnot, but, it certainly looks okay, I think. Again, it's kind of hard to tell because we don't really have a lot of good ways of analyzing whether lighting is looking correctly, but so from there, what I'd like to do is I'd like to just go ahead and introduce a flat weighting scheme. So let's suppose I just do like a W maybe, and I say there's going to be 8 of those, and then we'll just produce whatever those should be. Now, what you can see here is we transition on X first. So basically, we're going to have X and 1 minus X each time. Now, I'm going to show you a little trick that I like to use here to make these things more readable, right? And what I like to do is, let's just say we'll use the lowercase versions of each of these to produce the weight values for each of these. But what I like to do is I like to have sort of a plus and a minus version of each one, right? So I like to do something like this, right? And you can even do it this way if you want to. So like positive U and minus U or whatever, or negative U, either way. And so each of these is like which one of these you wanted. So if you wanted a positive X, right? I could even do X, Y, and Z would be another one to do it. So I don't know. You can choose whatever names you want for these. But what I like to do is I like to make the negative version of the thing as just a variable, right? And the reason for this is it makes it extremely easy to see what the heck is going on without actually hurting your eyes, right? So in this case, I know that the negative version of X, right, the one where it's inverted, is going to be on the 0, 2, 4, and 6 side, right? Because you can see that they would have been getting 1 minus the X blend. So if you look at what we've got here, and I can even put these in so that you can see them literally. If you look at what's going on here, we can say, well, 0, 2, 4, and 6, they should be getting the negative version of X, right? And then 1, 3, 5, and 7 should be getting the positive version of X. Make sense? So then we have to look and say, okay, now who's getting the positive and negative versions of Y? Well, 0 and 1 get the negative version of Y, right? And 4 and 5 get the negative version of Y. So I know that there's going to be a negative Y on each of these. Oops. Right? So it's negative, positive, negative, positive, negative, positive, negative, positive, and then negative, negative, presumably positive, positive, negative, negative, presumably positive, positive. And is it? Yes, it is. 2 and 3 have the positive version. 6 and 7 have the positive version, right? So there's my, positive y, positive y. And then finally on z, you can see there's just one z blend. 0, 1, 2, 3 all have the negative, and 4, 5, 6, 7 all have the positive. So we're negative z on each of these, and then we're positive z on each of these, right? So hopefully you can see it's really simple for us to build this weight table when you look at it this way. Instead of some giant tangle of crap that's really hard for you to understand, you can just see it's like negative, positive, negative, positive, negative, positive, negative, positive, negative, negative, positive, positive, negative, negative, positive, positive, negative, 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 positive, positive, right? It's much easier to see what's going on in this case. And then once we have those weight values, now the result just becomes a sum of the weights. So it's just tiles 0.value, right? And each of those is going to be multiplied by its weight. And I guess in this case, we might want it to look like that, just because it's a little easier. And so we can just now sum all of these up. And that's the actual equation that we needed. Right? So that should do, oops, don't ask me why there's a semicolon there. So that should do exactly the same thing, right? So this should produce literally no change, unless I screwed it up, which, often happens. But basically that's exactly the same sampling. It's just being computed in a slightly different way. And, the compiler probably turns these into the same thing once it does all of its SSA and, expression elimination and so on. But the reason that we want this transformation is that once we've put it in this form, we can now, for free, do normalization or knockouts or anything else. So, for example, if in here where we do compute voxel irradiance at, we have two choices. We can do really any number of things, but what we can do here is say, look, how did you want to compute this voxel irradiance? Do you want to just pass me in, for example, an F32 pointer where you're going to say, look, here's where the knockout values come from, or something, right? And I don't know exactly how we'd want to do this, but I'm guessing instead of a F32, I probably just want to take a U32 mask, probably even just a U16 mask here, I'm guessing. That would probably have come from, one of the external values we would have gotten, right? And so I don't know exactly how we want this mask to come in, but I think that's more or less what we would want. And probably what we want to do here is we just want to use the mask value to knock out certain elements of the voxel. So, something where we loft the mask up into some kind of a usable multiplier. There's some... It's kind of hard to say exactly how you want to do this because we haven't written this routine in SIMD yet. So again, I'm really just not sure how we want to do that. I'm trying to think. Because probably what's going to happen is we would do the classification wide and then, yeah, so, honestly, I think it probably will be something more like this. So you'll probably just use coefficients that come in. The coefficients will go like this, so they'll multiply on the back here. So you can devalue ones that you can't reach. And then when you're done with this, what we want to do is normalize these values. So we need to do a sum where we take each of these and add them together, right? so that we can produce the total value that we're going to get. And then once we know what that total value is, it's pretty cheap for us to invert it. And the only thing I'm not sure about here is, like, you know, if you're doing like a fast reciprocal, do we have... Yeah, so, you know, we have approximate 1 over, and, you know, I'm guessing that that should probably be what happens here. And I guess we didn't ever actually do one that doesn't use F32.4x's, which may be fine, you know, meh. So I'm not sure how I feel about that or if I care. So for right now, maybe we'll just say, all right, you know, maybe we do an RCP PS at some point, so we're expecting that we'll do this. For right now, maybe we don't. I mean, maybe we'll just do over this and let's put a to-do here, like to-do. Widen this path and use RCP because, you know, at the moment it's like, okay, we could still use RCP even just because it's a scalar, but we don't actually need to because we're not really trying to improve the performance of this particular path right now. We will eventually probably want to, but it's sort of a separate discussion. So we're going to have an inverse sum here, and we want to use that to multiply each of these values. And again, really all this is just saying, look, we need to boost all of the non-zero values to account for the values that got zeroed out or lessened by the coefficient that the caller requested. So it's really just this, right? It's really just an additional sum that tacks on the end. And because we know that that sum will distribute across all of the w's, we don't actually have to do it at that time, right? What we can do instead is just say, well, after we do all of the multiply sums, we can just do it at the end, right? Because whatever the lighting value that we got, we know that all of the weights would have been multiplied by this inverse sum, so we can literally just do one multiply at the end of the production, and that would produce everything we needed. Better yet, it makes it pretty easy for us to do this because since we probably won't be taking 4 samples at the same time because Intel chips have the absolute worst scatter-gather performance of any chip in the known universe. In fact, doesn't even have instructions for it till AVX. We know that we can't really do this path 4 wide very efficiently anyway. So at that point, it's like, well, since this is going to be a lateral sum, actually doing RGB at the same time is a cheap way to get 3x the performance through here, since I don't think we're going to get 4x the performance through here. So this whole thing could be done wide, and you could do the RGBs all at the same time. And so that's a nice way to think about how to widen this path in the future, in a way that might not be horrible because we'll get 3x, not 4x, but hey, it's 3x with literally no work. That's pretty good. Okay, so if I go ahead and build now, what we will find is that the F32C pointer is not going to be supplied by the people who actually need this to happen. So if we take a look inside the AAB raycast, which one's pretty, that's currently running, you can see us doing our compute voxel irradiance, and what we have is, you know, a missing parameter here. Now, the cheapest thing to do, obviously in this case, is just to say, look, there's 8 of these, right? Here's the, I don't know what we want to call this, but basically the gather coefficient or something. And we know that if we just set this to like all ones, that should be sufficient to reproduce the exact same thing that we were getting before. So if I were to do this, I should see no change. If we didn't screw up the previous path by the changes I just made, we will see the same rough lighting occurring as we march through the world. And that, you know, that does seem to be roughly what we're getting. I don't see really much evidence of any change at all. Don't quote me on that, but it seems about right from what I can tell. And remember, I think we turned off all the lights, so there's no lights where there actually are lamps like there normally were, because I think we stopped adding those. So we're literally just looking at the spread from this particular light, and at the moment it looks about the same as it used to. I don't see any indication that it's different. So hopefully we're basically getting the same thing, but I don't know. It's always kind of hard to tell. But bounce lighting wise, I don't know, like it sure does look like these tiles are getting brighter there. I don't know, but maybe that's just it's really, again, it's really, really difficult, unfortunately, to know like kind of what you're getting. We probably should put some strongly color altering occluders in here, so that we can see the difference between the direct lighting and the bounce lighting. So, for example, if I went into the push occluder code, you pass a separate color in here. So what I could do, and I don't really know if this will work particularly effectively, but what I could do is say, like, what if I just, instead of pushing occluder of the actual correct color, I just knock out all but the red component or something, right? So if you imagine doing that, then at least I could see a little bit. What is the complaint? Oh. Why does it take a V4? It doesn't use it, so that's odd, but okay. So anyway, if I knock out the other color components, I should now be able to tell the difference between things that directly sampled the white light source and things which bounced. And yeah, I mean, that's bounce lighting, right? I mean, kind of obviously is, in the sense that you can see it right there getting affected, by it. I could turn off the moonlight, just as another, just to force, so that we kind of know what we're looking at. I could say, moon color times equals 0, and that would just knock out any inbound lighting from anywhere else. So then you would get, this, and all of the bounce lighting that we see now is coming from just this one light source, right? So, it looks reasonable. It's hard to say. It looks reasonable. And you can see people doing back sampling here, right? That's what you're getting in some of these. So, I think that we're doing the sampling, but again, it's really hard to test. So as we do lighting quality, we're going to have to invent good ways of generating test cases because it's really hard to say. Right. And so as we move through the world using this particular test, you can kind of see what's going on here. And I mean, it sure seems like it's working, but again, it's really hard to say. I mean, I guess one thing we could do to test it is say, well, okay, so what if we went into this code and we intentionally knocked out a particular blend. So, suppose we said we only wanted reflections from one side. So we knock out, all of the things on the left side of the blend and only allowed things on the right side of the blend. That's one way of poking at this thing. And seeing what happens. So, I mean, that's a good test, right? That clearly screwed up. So I think that's good, really, because it means we've got an error in here, and we can go look at what's going on in there, right? So if we set these C0s to knock out certain parts of the of the blend, somehow that gave us a massively over-contributed lighting, which again might not even be wrong. It's hard to say, because we actually don't know if that's just because it caused us to like overweight certain values quickly, right, or something like this. So we don't really know, but it certainly shouldn't be the case that like our goal was to stably blend these together. So it's possible that this is just buggy, right? Like this is doing it wrong. And when these all added up to 1, which they were previously going to do, when they don't add up to 1, somehow this produces some kind of erroneously weird result, right? So since we have that, I'm going to go ahead and switch to a debug build so I can look at that routine and just see what's going on, because maybe I just made some stupid error that won't take very long to find. I don't know. It could be much more complicated than that, obviously, but let's go ahead and try it. So if I run the program now, and I guess I'm looking for compute voxel radiance at there. So where was my lighting code? Lighting. So if I want to take a look at that compute voxel radiance at code, that should probably be right here. Yeah. And I think we're running here. Yeah, we are. So if I wanted to look at this, I'm just gonna stop here, and I just want to produce what these weighting values are so that I can look at the weighting values. They look somewhat reasonable, I should think, right? It's a little bit hard to say because since the C values have pre-knocked out the other values, I can't see what they are, but I can just do this and see if that would have been a large value, and it was. So once we produce the sum here, you can see what it actually is. That's the sum of all of the values that have been added up. I'll be honest, that doesn't... Oh, because I haven't run it yet. I'm like, it doesn't look right. That looks right. And then we can see what the inverse is. And there we go. Now, I guess one problem that we'd have is if for some reason if we ever got a sample value where we knocked out the only values that actually were non-zero, then this inverse sum would be a problem. So I guess one thing I should take out, I don't really expect it to be happening, but you never really know, is I could just say, well, the inverse sum in this case needs to be guarded. So if the sum is greater than 0, we do it. If it's not, we don't. And maybe we even just give it a tolerance. So we're never going to produce particularly egregious values. And we'll have to see how we want to deal with that a little bit later. But let's suppose I did something like that, because I'm just curious if what we were actually seeing is just one case where we landed right on the dividing line, which could have happened. I'm just curious. What is going on? Stop. Build. There. And run. Okay, so I guess that was all it was we literally did have some that landed right on the boundary, because here's the lighting and it's working okay with that. Now, one of the really disturbing things about this, as I hope you can appreciate, is although you can see the sidedness, so let's suppose I stop right here, you can see the sidedness that is in there, right? As I move over here, you can see that it's really unlikely that you'll get stuff happening on the side, but it's very likely that you'll get stuff happening on this side. Well, actually, that's not actually probably the sidedness, to be completely honest with you. So I'll ignore that part of it for now. I was just going to say, you can see in here how we get some red sampling coming in, and we don't get any on this side. Whereas if I was to change it back, we will probably, presumably get that. So if I actually look at the gather C, and I change it back to all ones, I should see now red fringing on either side. But again, the thing that I wanted to underscore there was like, it was so subtle though. And so it's really kind of disturbing because you're like, it's so hard to see if these things are working properly, right? So now you can see some red fringing on this side, but man, is that like hard to tell. And so, it's really kind of one of those things that I think we're really going to have to, put on our thinking caps for, because it's like crazy that you can literally sample like totally wrong and it still kind of looks like lighting, that's just not, that makes it really hard to find the problems. And I just don't know, I just don't know how to verify that this is even remotely right at this point, right? It still could be like totally busted. And we just don't have a good way of knowing. So I do think that's another quality issue. It's like we're going to have to actually have a solid explanation of how the heck we know if this stuff is working properly. And at the moment, I really don't think we do. But I'm going to now go ahead and say, let's switch back over to the previous method. And I'm going to add in a thing that allows us to block light from coming from certain locations. Now, if I do the gather C here again, and I just stuff in the garbage values that we had, I think we're almost out of time too, so I probably won't have a chance to finish this today, but we can finish it tomorrow. If I go ahead and just do a quick build and run the game, what you will see, right? Oh, and that's kind of nice. You can see that the propagation is all happening in the secondary bounce because it's all red, right? That's pretty handy, actually, that change we made. So what you can see happening here again is like that spreading to outside the wall. I want to see if I can contain that by not allowing any of the light to propagate past the boundary that got hit. And this is actually not that complicated as a basis for producing this gather C value. And the reason that it's actually somewhat simple is I know where each of these gather C values comes from because they're known voxel locations. So they're just wherever I hit is a particular voxel location. And I just need to take the normal and I need to determine, and in fact, now that I'm thinking about it, I don't even know that I need to, really pass this in. I mean, if we're honest about it, I think we could probably produce it up here. I think it's a fairly straightforward computation that's just based on the position and the normal, right? Because I think all we need to do is take the wherever the voxel would have been, and we just look to see whether or not the thing you hit is on the same side or the other side of the place you're going to sample. I think that's actually all we need, right? Because again, if we just pop over to the board for one quick second, I can explain what I mean. If we were to do this and just think about doing it in 2D, because it's always easier to think about it in 2D than 3D, and they're the same. In this case, they're not the same in general. If you imagine we have 4 sample points that represent the lighting samples of our voxel. So here are like what the cells of the voxel would look like, right? What we're fundamentally asking is if we have a point and that point has a normal, we know that we're in one voxel cell, or rather, I shouldn't say we're really care that we're in one voxel cell. We know there was some origin point. And we know that we are viewing this, location. We know that we're viewing that from this origin point, right? So what we fundamentally want to know is, could we have seen each, of these things that we're going to sample, could we have seen them from this origin point based on this hit, right? And what you can see is, if I was to consider this to be a plane passing through here based on the normal, what I would immediately see is that for the origin, looking at this point, any of the voxel cells whose sample origin happens to be on the same side as the ray origin of this plane is something whose lighting probably could have contributed, right? Now, we don't know for sure. The most aggressive version of this sample gather is to actually raycast back from the sample point to all of these to see if you can see them. And people do that. That's an actual thing. But because we don't have the horsepower for it, we're just going to say, look, classify it based on the normal. Assume there weren't things like hanging around in here. But definitely don't sample things on the other side. Because if we couldn't make it past here, we sure don't want to sample it, right? So it's just a basic, simple heuristic to prevent light propagation in cases that we think are pretty solidly, obviously not going to work, as opposed to doing the more aggressive version, which is very expensive, right? So let's take a look. If we then go and look at the, what we were doing over here, we've got our gather C, and I'm just going to say, look, what we need to do is, and I guess what we can see here is that, hey, we don't have the origin as a classifier in this case. We kind of don't need it though, because we know that the normal has to point in the direction of the origin. So it's really just a classification on the normal. It's really just a classification to say what's going on with this, right? And I think that should be sufficient. Let me think about that for a second. I mean, there are other ways to think about it than that. Nah, yeah. So, you know what? Maybe we should think about this a little bit more carefully. So, what are we going to be doing eventually? Eventually, what we're going to be doing is saying we have a normal, we have a raycast that has hit this point, right? And we want to know, therefore, what would the bounce gather have been, right? And for a diffuse surface at the moment, what we're saying is we're just going to use how much light it would have given here, and we probably need a cosine fall off in there, right? And interestingly enough, we don't have one at the moment, but I think we do it on the outside. So, that's a lighting quality pass thing. And so if we're talking about light that could have been gathered from here, we kind of know that lighting coming from here is not super relevant, because obviously it could not have produced a bounce because it's on the wrong side of the surface. So I think all we really want to do is just classify based on the normal. Could it have come from someplace out here? And we could even be so aggressive as to cosine weight those contributions if we wanted to, right? So we could set the W values to actually be these C values to not just be 0 or 1. They could even be cosine fall-off angles. I don't know if we really want to do that, but you can see where I'm going with that, right? So if we wanted to do that, what we could do is say, well, for each of these, and you can see this get tile clamped thing here, right? If I go to get tile clamped, You can see what I do here is it's just producing it's just looking up into the voxel for each of these positions. And since I can pretty much directly determine what the actual voxel value is in each case, and I don't even really need to because I can just do it in relative voxel space, I kind of can just use the normals. I can probably just even use the sample P. Well, can I do that? I'm trying to think if there's a way to avoid actually doing the subtract. So if you think about what's going to happen here, right, the sample P is going to give me you can think about the sample P as now having been mapped into the voxel, right? So what I'm going to end up with is I'm going to end up with something where I do have a normalized inside a voxel. I mean, I can even just look at it this way. I'm going to have a normalized coordinate that's the UVW, right? So I'm going to have one in here that's like UVW, right? And then I'm going to have a sign of my normal, right? And I think because it's already been mapped into the space of the voxel, I think that means all I have to do is just read the sign, right? Because I've already put it so that this is the basis, the corner for, I've already figured out which corner it is because we mapped it into the voxel. So I think I already know, well, whichever direction this thing is pointing, I just need to grab the things that are cited properly with that. So if the voxel x is positive, if the normals x is positive, then I think you just grab these, and if it's negative, you grab these, would be how that would work, right? Trying to think if there's how this would work exactly. So I guess the problem is, depending on how far this is, you don't really know. So I mean, let's suppose it looks like that, right? Versus the same exact plane, but up here, you would produce different results. So unfortunately, I do think you have to do the subtract. I think you have to do the subtract of the UVW. I just don't see how else you could really do it. Right? I mean, I don't really. I don't really see a lot of options there. And I could be missing something. But I don't see really what else you could do. So I think probably what we need there is just like, you need to do the inner product of the two directions. So you have the normal and you do the subtract. You do the inner product and then you can see if it's less than 0, So again, I don't know exactly how we want to do that. And whether we want that to be a fall-off based thing or not. But if you imagine building this set of results here, you're going to end up with something that looks like this, which is like the, I guess the product. And in fact, I could actually just do it this way. So here's our coefficient values. And we know we have the UVW, and so then we know like each of the different locations that we're doing a subtraction from. So in this case, we would know that it's like, it's UVW, whatever it is, minus the V3000, which of course will produce exactly the same value. And we just need to take the inner product of that direction with the normal that we're actually sampling, right? So the sample normal, that would tell us that would classify each one of these things relative to the surface, right? So if we take each of these, and we know, we do an X move for each of them here. We know we do a Y move for each of them here. And a Z move for each of them here to line them up with how we did these. In theory, this now gives us that inner product fall off, and we just have to then decide what we actually want to do with that inner product fall off. Do we want to use it and just clamp it to 0, or do we want to force it to be either 0 or 1, meaning we don't actually smoothly fall off? And I'm going to go ahead and say, since we're bothering to calculate it, let's just try the smooth fall off. So I'm going to say, the heck with it. Let's just do a clamp 0, 1 on this, and we'll just kind of produce those values like so. At that point, we don't need to pass in the weights because it looks like we can just produce reasonable weights directly from that process. So I guess this just goes away, which, hey, that's great. If it turns out that's really something we don't have to worry about, I'm pretty happy about that. Means that these just aren't necessary, and the less things are necessary, the better the code. So I think that's all we need, and we can now see to what extent that's working properly. We probably have to do some testing. I don't know exactly what we want to do there, but so here's it with the barrier in place. And one of the things you'll immediately notice is this, I believe, was the code that was spiking directly. So that did the feedback, the bad feedback loop. And one thing you can see is it's not doing that now. And these are not getting those values, right? So that's a pretty dramatic quality improvement. Not only did it do the thing I wanted it to do, which was to prevent light leaking into the bottom, but it also kept the spiking down dramatically. In fact, it still spikes a little in certain places, but so that's just a really good sign, right? We're still pretty far from having a good result, but it's pretty great that just that alone is doing it. And you can see, look at those are all nicely clamped now, and we're not getting any leaking to the outside. So that's a pretty dramatic improvement. I think that's a good place to stop for today. And tomorrow what we can do is take a look at the cube casting to start to work on how the actual light values should be maintained, because it looks like we're sort of getting a little bit closer to having those values be sane as we go, right? And I think that's good. So again, just to recap a little bit too, I said this last week, but I'll say it again. Not a big fan of unit tests. I think they're mostly useless a lot of the times. And when you can isolate a circumstance where you really can write one effectively, they're great. And I don't dislike them at all. I think they're fantastic for that. But most of the time, the more productive type of coding to do for testing is visualization. And the reason for that is twofold. One is it can help you debug things that unit tests just can't address because it's very hard to figure out how you would ever write a unit test. But the far, 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 far more important aspect of it is it gains you insight into the problem, and unit testing never really does that. So when you spend time on visualization code, you start to see things immediately, like I saw the inside the wall part of things, I saw the fact that these things down here were getting lighting. Those immediately allow me to start improving my algorithm that have nothing to do with whether it was behaving in a way that I could have defined ahead of time, because this is all approximate. I don't know what the correct definition is for the lighting in this case. I really don't. I could compare it against a ground truth reference raycast, but I know we'll never be able to produce something that matches that sort of thing closely, right? So at the best possible case, the thing that the unit test could have done is just told me that I had the lighting wrong there, but it wouldn't have told me what would have been the ways to start modifying my algorithm to get it closer. This kind of visualization is so good precisely because it allows me to start attacking the problem using entirely new insights that I didn't have before I started, right? And so I think the challenge for our next step, as we try to get the lighting looking really nice, is to figure out what kind of visualizations we can use to visualize how the lighting is flowing through the voxel so that we can sort of build our intuition about how those values should work and how they can stay stable over time, right? And that's really something that I think will push it forwards further. But I'm really happy with where it's at the moment anyway. It's also not that expensive, and I think we'll be able to run it at 60 frames a second without too much effort as well. In fact, it might already be running at 60 frames a second, actually, because if you look at how much time is currently spent on the debug, you can see that actually if you chopped that off, you'd probably be at 60 frames. So we should draw a 60 frames a second bar in there, but it's pretty close. And at the very least, you run this on an i9-9900, and this is 16 milliseconds, no problem, because we would have a whole bunch more threads to use as well. So I think, because I don't remember, I mean, correct me if I'm wrong, but is this? Yeah. This is 8 fake cores, 4 real cores, right? So 4 real cores, but 8 hyperthreads. The modern Intel line, not to mention the AMD line, which is way better on core count, is already at 8 real processors. So, as machines get faster, our lighting gets dramatically faster because it's completely parallelized. And so I feel like, to a certain extent, we're already at 60 FPS in software just by upgrading the machine, right? So that's a good place to be as well. Let's go ahead and go to a brief Q&A, and then let's also talk I don't know if Abner's still here, but we can also talk about Handmade Seattle. That's the cube ray tracing that was just running. So if you look, that was the cube ray tracer that I was just running. Do you have any suggestions regarding how to study and better retain information? I remember you said you learned math only because you realized you needed it to program things, so particularly in relation to math. Do you have any advice on how to learn in ways that are more efficient? So I guess I don't have a lot of specific advice because I think it depends a lot on how your brain happens to retain information. Different people have different affinities for like how they will retain information, and so I don't think there's a universal wrong or right way for that reason. There are certainly probably ways that will never work for anyone, and there are probably some ways that work pretty well for everyone, but then I suspect there's also, for every individual, they probably fall into one of a few camps of learning. And if you happen to pick a technique that works well for your camp, you're going to be a lot more effective than if you say, so, if you and I have slightly different learning, brain chemistries or whatever, then if you follow exactly the way that works best for me, it may actually be slightly slower for you than if you follow the way that works best for you, which would be slightly slower for me. So I do think you have to be careful taking advice from people, because if those people don't happen to learn as in the same way that you do as effectively, you may just be artificially hindered by that advice. So I think the broader advice I can give you that hopefully would apply to everyone is try to self-analyze as much as you can your learning processes, because if you randomly try some stuff, so read the chapter of a book on math that people say is a good math book, right? How well did you retain the information? Do the exercises. How well did you retain the information? Now try a different scheme. pick a programming thing that you want to do that involves math. Learn the math for that and write the program that solves a problem, working it through till you get the right answer, right? How well do you retain the information now? How much time did each of those take versus how much information right? Spend a month or two doing the experimentation to see how you retain the information, right? Because learning how you learn is something you can then apply forever, and it will always be worth your time to spend a month or two figuring out which way helps you retain it best. So I would advise against taking someone else's recommended approach, and I would instead recommend trying a number of approaches, because it's obvious that there are a number, and you can just read a whole bunch of people's opinions on it and just write down all the things that they said as different possible approaches. Try them and see how it sticks in your head for a variety of different learning methods, and then whichever one seemed like the best bang for the buck, so took the least time for the most amount of retention, that's probably what you're looking at. For me, I learned programming when I was incredibly young compared to most people, I guess even today. I started programming when I was 7. What I think that means for me is that my brain is probably more hardwired to think in terms of code than most people's. So for learning math, for me, I have to write the code. I simply do not learn math from math, ever, at all. It doesn't happen. So for people who learned math first and programming second, something like that could be inverted, right? But for me, because I learned programming incredibly young, way before I knew math at all, I don't even know if I knew addition, let alone multiplication. I mean, when you're 7 in the US, you're a long way from being at the point in school where you learn multiplication tables, right? I think you learned multiplication tables, I want to say in 4th grade in the US, for me. And I had been programming for years by the time I learned the multiplication table. The multiplication tables, forget algebra, just how to multiply, 9 times 7, right? So if you think about the difference between those two things, it I think becomes fairly obvious why, for me, I've got to write the code, because I think my brain that's how it works. It's a procedural brain. It thinks in terms of steps. It doesn't think in terms of equalities. So if you present me a bunch of stuff in equations, I just don't think that way. It's not going to help me. Equivalence isn't a thing my brain understands natively. It's a thing it had to learn later that's kind of foreign. Procedural, the way a CPU works, is native to my brain. My brain thinks through problems as assignments, not equivalences. And so at that point, it's just, for me, math is inherently foreign. It always will be. And so I always need to translate it into some procedural version that evinces the concept in order for me to really, I think, fully internalize it as a thing I can use. And that may be completely inverted, I bet, for some people. If you learned a lot of math or spent a lot of time doing math before you ever learned programming, I would be shocked if the opposite wasn't true for you, right? But I could be wrong. When you're building the weight table, why were the negative values 1 minus UVWX instead of 0 minus UVWX? Sorry if you already answered this. I tuned in late. Yeah, you should probably go rewatch this episode when I post the VOD, hopefully later today, because I walked through exactly how the linear blend works in this case, and you're going to probably want to watch that whole thing. I explained it in complete detail, and I think it hopefully will be clear if you go watch that. Yeah, I mean, I guess what I would say is, if you go take a look at the complete explanation from this episode, I think it should tell you exactly why it's 1 minus. But if it's not, you can always come back tomorrow and ask me, and I'll happily go over the part you didn't get from today. The NVIDIA paper you were using in the beginning was using depth info on the light probes to avoid light leaking. Is this something you might also want to try? So I want to, if I can, I want to get away with not doing so. The reason for that is that storing that information is going to be an additional cost for us, and I'd really like to not do it if I can get away with it. The NVIDIA paper has loftier goals than do we, right? They were doing research and they were trying to produce they were trying to do as high quality work as they could, right? But I don't want to do additional ops that I don't have to do. And if you have to start storing the depth map, that's just a lot of extra work, right? So I'm hoping we can get away without it because we don't need to produce particularly accurate lighting. We're just trying to produce lighting that we think looks good for our game. And it's already getting there. So I'm hoping that we can just not. If we have to, we have to. But, you know. Oh, Abner said the info was on the site. He had to go. Okay. So I guess it's too bad Abner's not here because I was going to ask him some questions about the conference, but I'll just mention it anyway. I'm sure there'll be a lot more information, and I'll mention it on stream more prominently in the future. When it's more of a going concern, I guess. But I just wanted people to be aware of the fact that Handmade Seattle, I think that's the web address. Is it an org? Yes. No, it's a com. I don't know. So Handmade Seattle, which was the conference that Abner organized last year, which everyone said they loved. As far as I could tell, I heard many people say that they thought it was great. Was going to be done again. He even said at last year's conference, he was like, I'm going to do it again next year. Obviously, because of pandemic concerns, everyone assumed, including me, that it would not be happening this year, but it turns out it is happening this year, and he's just going to do it as an online event instead of as a thing where you actually go in person, which obviously would have a tremendous amount of risk associated with it, both in terms of the air travel. Lots of people come from overseas for Handmade Seattle. And so this just got announced. It was like yesterday I saw the email. And what they're doing, or I guess I should say what Abner specifically is doing, this is Abner, what they're doing is it is going to be free, which is kind of awesome. But there are going to be tickets to help fund it and, of course, pay for Abner's time. He does all of this basically just out of the goodness of his heart. If you go to the page for tickets here, which will be going on sale, I guess, where is I don't actually know. There was a thing. So I guess they'll be going on sale in 3 weeks. If you go look at the tickets, what's going to happen is basically there's sort of a virtual attendance that will happen. And it's like kind of to gate it so that it's not a Twitch chat disaster. It's basically like if you buy a ticket to the conference, you will be able to like ask questions like as if you were attending, right? And so everyone can see it for free, but if you want to actually attend and ask questions and participate, then you buy a ticket, and the ticket will get you access to like the private chat server where the attendees are asking the questions and interacting with the people who are presenting and so on, which I think is a great idea. So just wanted to let you know that that's coming up. Put it on your radar. There'll be a lot more announcements about it as it actually becomes a thing. As you know now, it's literally just a website right now. You can't even buy the tickets yet. So when it gets closer to the time and the tickets are actually available, I'll make sure to mention it again. But just so you know, if you want to interact with Abner or whatever, check out the Twitter feed or look at what's going on. That's what's going on, right? So that's basically the situation, right? Any thoughts on the Nanite Unreal Engine demo? Yeah, I covered it previously. It's just we didn't record it because I didn't know if there would be... Like, I went through the demo with people and I kind of explained what was going on. I didn't record that, or at least I don't think I have it recorded. It might be in the Twitch back capture. It probably is, actually. So if you're a subscriber to the Twitch channel, you can probably go to the back catalog and watch me discuss it. And it was actually kind of funny because, amusingly, I was like, what they're probably doing here is this thing, and I pointed to a paper, and then someone on the chat was like, actually, they posted that they specifically were using that technique, and I'm like, oh, well, good to know my guesswork is still on point. So apparently, they are doing exactly what I said they were doing, but I didn't actually know that when I said it. My common way to see math and programming is to see the subconcepts of the concept trying to learn and do like a tree until I get the leaves, which are concepts I already know or axioms. Then I go upward from there and try to specifically understand the how and why of the concept connections works well for both programming and math. I can't say I really do it that way, but it does sound like a reasonable option. Build you strong. Could we just create a distance limit to stop bouncing light? We could, but I don't really want to because light bounces as far as it bounces. I mean, light itself doesn't attenuate absent a participating medium. That's why you can see stars. So you don't really want to simulate light that way if you can avoid it. But you know, we actually do have some stuff in there to make computation easier. We do use a sort of bucket brigade approach to avoid having to traverse long distances on the raycasts. We already do that, though. In what way does a custom engine affect the feel of a game? Is it always a question of having better performance or allowing for more flexibility? I've always thought there's nothing you can't do in Unity or Unreal. It's just going to be slower. So that's a really, I want to say deep question, or rather the answer is kind of deep. So here's what I would say. I think people don't appreciate just how bad it is to use a pre-made engine for a game. And here's why. While it's totally true that there's plenty of circumstances in which you just don't have a choice, right? Because it's way too much work to build an engine these days. Computers and gaming are just too complicated. So I don't begrudge anyone the decision to use Unity or Unreal. Like it's a very difficult choice to say we're going to make our own custom thing, right? So I don't think it's a bad decision to do so. But what I do think people have to understand is just how costly it is in terms of what you are capable of making. And the reason for that is because when you sit down to make something, what you are given as your medium has a dramatic effect on what you can create. Because all of the decisions that were made in every aspect, whether it's how you make models for the game, how you import them, how the world is created, how the world is stored, what the representation for the logical entities are in that world, what the way in which the scripting works or how it is input, every single one of those things. Each one of those decisions makes some game designs hard and some game designs easy. And when you're talking about an engine with literally hundreds of thousands of decisions having been made in something like Unreal or Unity, you're talking about a situation where a whole swath of possible games are very hard to create, while a whole swath of possible games are very easy to create. And I think it overwhelmingly leads games made in these engines to feel the same. And I think the proof is kind of in the pudding there. Like, I don't know about you, but when I play games these days, they all feel the same. It's weird, right? You play 10 games that look completely different. Like, the graphics are obviously completely different. They have very different styles. And when you play them, it feels like you're playing the exact same game. It's eerie. And you can't even necessarily put your finger on it because they're definitely different, right? But I think the problem is once you make this decision that it's like, well, I'm using Unity's system and I'm creating the entities in my game with Unity's entity system and its definition of an entity and what an entity can do, I think it just overwhelmingly funnels people towards making things that feel a particular way. And one of the most interesting experiences that I have had in recent memory is I went home to visit my parents a year ago, 2 years ago. I don't remember how long ago it was. Obviously, I go to visit my parents, often, but this was one particular time I went home to visit my parents. And I happened to take out a ColecoVision. Now, a ColecoVision is one of these. It is a video game console, and it was the video game console that I had as a child. So when I say we took out a ColecoVision, I literally mean we took out the ColecoVision that I had, that my parents literally bought in like 1982 or 1983, right? Like, we had one. And when I played the games on this ColecoVision, I had to try to sort of repair the controllers. They were kind of corroded and not really working and broken, but I repaired them best I could. I played maybe 10 cartridges or 12 cartridges that we had for the ColecoVision, and every single one felt completely different. It was shocking. Like, Frogger 2 felt completely different from Venture, felt completely different from Pepper 2, felt completely different from Ladybug. And the variety of games that people seem to end up with when they had to write the whole game, there's something wrong with our current way of doing things, and it seems kind of just obvious, right? And so the main thing I would say is not so much that using Unity or Unreal or something like that is a problem because there's some better performance or something you're going to get out of your engine. And that may be true. I mean, if you write a bespoke engine for something and you're really good at it, obviously you can outperform Unreal or Unity. I mean, there's no question. Making a general purpose engine is much harder than making a special purpose engine, so their job is harder than yours just by definition. But I don't really think that's the biggest concern. These days, I'm thinking the biggest concern is that the tools you are given to make these games force you into making the same damn game. And the result is 7,000 games a year, literally, and I feel like there's no new games a year, right? And it's really depressing. So, I don't know, right? And so that's unfortunate, but that just feels like what's happening. And I don't know. It could just be not that. It could just be that because there's 7,000 games a year, it's really hard to find the 2 or 3 that are actually different. Whereas on the ColecoVision, when there was only 100 games a year, you were probably going to find the 2 or 3 that were actually different, right? So that's another possibility. It could just be that the signal-to-noise ratio has become so terrible. And that's a reason why I wish engines didn't exist in that case, because then there would be far fewer games maybe. But, I don't really think that's the case, because I feel like I would probably hear about them if there were really interesting games coming out, and I don't. So I don't know. I mean, I could be wrong, but and just in terms, like someone was saying, like I would argue it's not the fault of engines, but rather lazy devs. I mean, not. Again, I don't really think it's appropriate to blame somebody for it, right? It's just how it is. And I don't necessarily think you can accuse developers of being lazy because, I mean, they may not even have the capability to do otherwise, right? I mean, if you really wanted to make a creative new game design inside Unity or Unreal, well, you're basically rolling your own mini engine inside their engine and then having to make a shim that converts kind of to their idea of how everything is stored and all this other stuff, right? And that's incredibly difficult. I mean, the point of having pre-made engines was supposed to be that people didn't have to learn all of the stuff that we cover on Handmade Hero, right? Like, that's the point. And I think the unfortunate reality is you really just can't have it both ways. Like, if you are capable of doing all this stuff, then yeah, sure. You know, your choice is pretty much anything you want. You could just roll your own engine. You could decide that, well, I can make my own mini engine inside of Unreal and then just leverage their renderer or something, right? You can make creative decisions like that to save yourself time or whatever else you want to do, and you can. But the number of people who can do that is very small. All of the people who have kind of been told that, well, you just use this engine, you can make your game. I mean, I think, unfortunately, they're not being lazy. They're all they know is what can be done in that. Like, they don't have the knowledge or capability yet to understand that there are things that they can't do, or even that their decisions are being forced in a particular direction because of these engines. So I don't consider that to be laziness. I consider that to be not having provided the materials or not understanding well enough as an industry what the differences are and what actually is happening there, because it's not obvious and it's not clear. So I don't think it's fundamentally the case that there are developers that are being lazy here. I don't think that's true. I think there are people who are making a particular business decision who perhaps don't realize necessarily what that entails and how that will affect what kind of games they ever end up making. So I think that's true. But I also think it's just, as an industry, we don't understand these things very well. We don't really understand what kinds of games don't get made because of all the people going to pre-made engines, right? So it's really, I think it's incorrect to call anyone lazy in this scenario. I think it's a question of understanding, and we don't understand it very well. And yeah, I mean, to be honest, I also disagree with the opinion that it's an issue of uncreative games coming from people wanting to make money. I don't think that's true either. I think there's a tremendous number of fairly earnest games that are not cynical, they're not money grabs being made in Unreal and Unity, and they still just feel really derivative and samey. Even from people who are developers who are specifically trying to stand out and do something different. And it just doesn't. And that's because the gameplay, the actual thing you feel, like they may take a bold art direction, they may take a bold narrative direction, but what they fundamentally can't do is take a bold actual game direction, because Unreal and Unity are fundamentally only suitable for building very specific types of games that are more or less games where there are independent entities floating around in the world with a physics engine underlying them of varying degrees of responsiveness that you then interact with by entity touches entity events. Like, effectively, all these games are collision-oriented, event-driven games. And that's all we make, right? And breaking out of that is very difficult when you use these engines, because you will be forced to write everything yourself, right? If you choose to do so. And most people who go into that would not know how to do that for any non-trivial game design. I mean, I think to a certain extent, one of the things that I think is really interesting to me, just really, really interesting to me, is if you take a look at how many people have clearly taken the direction that John Blow went in Braid, the 2D platformer, but that has a much deeper underlying set of game mechanics that get exposed, right? Effectively nobody, despite like hundreds, if not thousands, of games that clearly descended from this idea, almost none of them have any gameplay of that kind, right? Almost none. And that's because it's incredibly difficult to program all this complex, like the simple thing that's in Braid that all it was saying that the time that the t-axis of the game and the x-axis of the game were the same now, right? That alone would be a tremendous amount of procedural programming knowledge someone would have to do that, even if they had Unity or Unreal, just the whole thing in front of them, right? So almost nobody does. And you can, right? It's not that you can't, if you know what you're doing, do these things inside there. But because people start out and all they know is Unity or all they know is Unreal and how to work with those systems, they never learn the skills that would be necessary to do those things. And so that's a big part of it, right? And it's really, really difficult to get to those points. And I think if it were easy, we'd see a lot more games that could do it. But as it is, we see few, almost none, maybe one or two sometimes. I'm blanking on any examples right now, but once in a while you get someone who does do them, and I suspect those people probably came from a programming background where they knew more, and so they were able to say, oh yeah, like I'm going to do this in Unity or Unreal, but I'm going to write this whole substrate that sits on top of it, that lets me create that kind of interesting gameplay. You know what I mean? And even those games probably don't have nearly as much as Braid had, I don't think Superhot did do that. Superhot is just multiplying the time step by how fast you're moving. It can't rewind. Like, it doesn't go backwards. Which in Braid's, in that particular case, in Braid's level, forget the rewind. But in Superhot, you can't move backwards and have the bullets retreat, right? So it's not really the case. So... And yeah, I mean, I don't have a prescription for this. And to some extent, I also don't care. I mean, except from the perspective of being a game player myself, it's depressing to want to play a game on the weekend and they're all the same. I feel like I've played them all already, And so, but I don't care, I guess, at some level, other than the fact that I wish there was more creativity, but, whatever. But yeah, I would say... maybe something that the industry can consider doing is actually trying to spend more time being cognizant of what Unity and Unreal are making easy and what they're making hard, and start trying to actively push on those things. Like, try to figure out how you can make games that are looking at what am I not doing because it's not something that's a checkbox on Unity and whatever, right? And try to push towards breaking more of those barriers, All right, let's do last question. Have I ever worked with HRTF-based audio? And the answer is no, I have not. I haven't actually ever seen the demo that convinces me I care about HRTF audio, but I also haven't really been looking. So I'm totally willing to believe that at some point we'll get to a really high-end ear response sim kind of a thing that, yeah, I mean, that maybe at that point you're kind of, yeah, I don't know. I mean, I really couldn't tell you. Like, I don't know if I think it'll ever really be that relevant, but I'm willing to believe that it will be at some point, right? So. Also, I guess I would point out there's some mention of Cyberpunk 2077. That game's not out yet, so I mean, obviously you can't have an opinion about it, right? But as far as anyone's shown, it's just exactly the same thing as you would expect if you were playing any other game that was literally exactly the same way. Like, it doesn't look even remotely like it's doing anything with gameplay that's any different from exactly what you could have built in the Unreal Engine. Now, obviously, I think it's great that they do their own in-house engine, because I think the more engines, the better. But there's literally nothing in the Cyberpunk 2077 demos that doesn't suggest it's literally exactly something you could have done in Unreal. And, I think that at least the UE4 stuff has a much harder time with expansive environments, and I think that the CD Projekt Red people have done a much better job with their engine in terms of expansive vistas and stuff like that than the. So I actually think CD Projekt Red have done a fantastic job with their engine. I think they're a great engine dev. But in terms of gameplay, it's exactly the same thing that you've played 100 million times before. And, I will probably play it because I don't mind playing a AAA game once in a while. I played Horizon Zero Dawn, for example, a couple years back. Had a good time. And so I think playing AAA games can be fun sometimes because they present this big, expansive world with tons of art, and it's nice. The gameplay is exactly the frickin' same. I push on the analog stick to move my dude around, or in Horizon Zero Dawn, my lady around, and then I push on some buttons to fire projectiles, and those things hit and do something. That's the whole game. It's asteroids 24/7, right? And I will be absolutely shocked if somehow Cyberpunk 2077 doesn't feel exactly the same way, right? I mean, that's what we write. We don't write anything else here. And there's the little part of the game that has the 3-choice dialogue tree that someone's got in there, right? I mean, we know what all these things are going to be. I don't need to play Cyberpunk 2077 to tell you everything that's in Cyberpunk 2077, because if there's one thing I can tell you for sure, it's that 100% of the things that you saw at the PS5 reveal are games I can already tell you exactly how you play them, right? Because that's all we build. And it's not bad, right? It's just we have to recognize that's what it is. All right. Thank you, everyone, for joining me for another episode of Handmade Hero. It's been a pleasure coding with you, as always. If you would like to follow along the series at home, you can always pre-order the game at handmadehero.org, and it comes with the source code so you can follow along with me as we build it. I will be back here tomorrow when I will start to look at some other lighting quality things that I'd like to look at with our Cubecaster. I was really pleased with the progress we made today. Everything kind of went almost better than I would have expected. And so I feel really good about our prospects for taking some more steps down that road. And the lighting is starting to come into a place where I'm thinking it might actually be kind of nice and we can finally sign off on it. It's one of the hardest things we've done on Handmade Hero. It's a really, really difficult problem for all engines. Even, the very latest game engines, cutting edge game engines have a tremendously hard time with indirect lighting. You could even go see, if you look at the most recent Unreal 5 demo that they showed, it has several frames of lag on indirect lighting changes. It's just, that's how hard it is. It's a very tough problem. But I think we're doing a reasonable job on it, and I think we can start to converge now on a good solution, because everything seems to be falling into place relatively well. It was a hard road to get here, but I think we made it. So I'm excited for that, and hopefully you'll be back here to join me. Until then, have fun programming, everyone, and I'll see you on the internet. Take it easy, everybody.